Good evening, ערב טוב.
ערב טוב.
בואו נחכה עוד 2-3 דקות.
כן, יש כמה שבדיוק אמרו לי שהם מחפשים את הקישור והצטרפו.
אוקיי. Okay, ערב טוב. Good evening again. Let's start. Hopefully others will join us. Just 1 second. Okay. Yep, okay. You do see the Mentimeter, right? I want a few more responses.
Yes,
Hungry. I cannot help with that. Tired, I'll try to finish earlier. We'll see. All right. Okay, so it's working. Everything is good. Good evening, everybody. And let's start. So we talked about replication crisis and meta science already, and I just want to demonstrate that these are indeed very lively topics that are ongoing. So this, for example, was published in PNAS last week. Very interesting paper. It's submitted as a regular science paper, which is peer-reviewed, and the title says, productive scientists are associated with lower disruption in scientific publishing. Please open your mic and tell me in free language, what do you think this paper is about and what does the title basically claims?
Perhaps it's related to what we discussed last time, but less struggles upon getting a paper published may be beneficial for the community and the writer itself.
Less what?
Less, let's call it struggles along the way. Less
No,
steps you need to follow, or I don't know.
that's not what it is about. More ideas? By now you could kind of read the abstract, but I'm not sure the abstract is that clear either. Any idea? What is scientific disruption?
Too many papers?
No?
No.
Other ideas?
It changed the way that the researchers organize their research.
Again?
It changed how the researchers organize their research.
So this is a paper that is so
Disrupt.
different and important that really disrupt the whole community. Groundbreaking paper. So basically what the title says in a very PC way, that scientists that publish a lot don't disrupt. They don't have good papers. They just publish a lot. And if you want to really make a difference, take your time, think carefully, do the science properly, and only then you'll be able to be disruptive. The disruption usually has wrong connotation. It sounds like negative word. In this case, disruption means good, means that you really did some amazing scientific work that disrupted the field and changed the course of, thinking, the main course of thinking in the field. So they actually use statistics and scientific methods to prove that people who publish a lot don't disrupt. Okay, so this is just from last week, very related to things we discussed. All right, this is another paper from Science. Actually, this is, I think, this week. And just we said that the replication crisis is an ongoing issue. And here is in the news, they basically set up a server where you can basically follow up all successful replication attempts. So again, we are trying to do science better. Those are very current topics. And maybe you make a habit now, since we introduced this concept, each time you open a Science or Nature or PNAS or a physical review, whatever, look at the first few pages, and I guarantee you will find meta-science and replication crisis commentaries, op-eds, and so on, because these are issues that really occupy the scientific community as a whole. Questions so far? Okay. So what we are going to do today, we are going to go over Watson and Crick paper from 1953. Most of, or if not all of you, are physicists. So the first question I want to ask is, we are going to discuss basically 3 papers related to Watson and Crick. And if we have time, we'll talk about the Forster paper. So the first thing I want to ask is, did you read the paper? If you did not, don't be shy. I just want to know for my own knowledge, how many of you read it? Maybe you can also open your mics and tell me, have you ever read it before, or this is the first time you see this paper?
For me, it was the first time.
Okay. Others willing to share?
First time.
First time.
For me, first time.
First time.
Also first time.
All right. So we already achieved our goal. That's great. Now let's go over this paper. Maybe before we start, what do you think about the paper?
Very good.
Okay. Was it understood by a non,
Yes.
you are not in the field and you could read the paper?
Yes.
Yes. Others?
Can you hear me?
Yeah.
Yes.
So, sorry, can you hear me now?
Yes.
It was a great paper, but I felt relatively to physics paper, it was lacking like proofs to show that what they are saying is true. But I
Yeah.
suppose,
Well, we'll talk about this. This actually relates to the way science was done in the 50s.
okay,
Okay.
great. Thanks.
Also, the way it's written is very different. It's like talking about other people work very explicitly.
Okay.
I think it was hard to read. I'm not in the field, and I think
Yeah.
it's
Okay.
yeah.
All right. Good. All right. Let's start. All right. So here is the paper we're discussing. The title is Molecular Structure of Nucleic Acids. It was published in Nature in 1953. It's actually a one-page paper. Look at this. This is the paper. It finishes here. Here are the references. Can you publish in PRL a one-page paper nowadays? Okay. So this is a very famous paper, of course. It studied many things, most notably, it studied molecular biology. It's responsible for the Human Genome Project. It's responsible for gene therapy nowadays. It really was a revolution. We'll discuss this. Many people compare this paper to Newton's paper. So this is as important in biology as Newton in physics. So very, very fundamental paper. How many of you know that this is not a single paper? There was actually 3 papers back to back published. But only this paper is very well known. So here is a second paper by Wilkins, Stokes, and Wilson. It's basically immediately starting here after the first paper. This is 2 pages. And there is a third paper, and this is by Franklin Gosling and Gosling. And it follows the second paper. So there are 3 papers all talking about the same things and all talking about the data shown here. Data that was taken by actually Rosalind Franklin, not by Watson and Crick. So oh, we have a visitor again. Molecular biology, huh? That's the future. Okay, why only Watson and Crick paper is so well known? The other 2 are less known. Any idea? Written concisely. Very nice. Simplicity. How about they got the Nobel Prize? Other ones did not. Lots of citations. Written well, very important. Okay. Any other comments? If no, we'll move on. Okay, so what I'm going to do next, I'm going to actually go through the paper with annotations that were done by the staff of a very famous science museum in San Francisco called the Exploratorium. Anybody heard about the Exploratorium? I used to be in the Bay.
No.
Sorry? It's
No, just
go ahead.
no. I was just saying that I'm not familiar. Not
Okay.
important.
Okay.
Sorry.
So I am very familiar because when my kids were very young, that's 35, 40 years ago, I was in Lawrence Berkeley National Laboratory next to Berkeley campus. We spent a lot of time in San Francisco with the kids. And that was the science museum in the country at that time because it was hands-on and really very, very good. And one of the exhibitions there was about DNA. And they actually analyze the paper. So that's what I'm going to discuss now. We are going to go through that annotation. And all the points that you raised and many more will be raised. So let's start. So here the paper, we wish to suggest a structure for the salt of deoxyribose nucleic acids, basically DNA. The structure has novel features and so on and so on. So let's go through the comments. First of all, Watson and Crick. I'm not going to read everything here, but this is basically telling that the two guys were very, very passionate scientists. They were in competition with Linus Pauling, who was in Caltech at the time. And they got, go ahead from their boss to try to beat Linus Pauling because Linus Pauling was the first to solve the structure of a protein before the structure of DNA. He was a physicist in Cavendish lab in Cambridge. And they were basically the first people to basically use X-rays to start to solve structures of macromolecules. So it was very clear that the DNA carries the genetic code. There were many experiments before suggesting this. And so everybody felt that X-ray is the right tool to try to solve the structure. And if you solve the structure, you understand how genetic information is basically replicated and manipulated. So these guys were really, Watson was a very young postdoc who came from US to Great Britain. And Crick was a physicist with experience with X-ray diffraction, and they started to work together. This is 1953, and this is really the date that marks the birth of molecular biology. And from molecular biology, of course, you have genetics, you have microbiology, you have cancer, you have nowadays CRISPR-Cas9 for gene therapy. It was really a revolution. Again, as I made the comparison, it's basically Newton laws for biology. So that starts in 1953, and we are basically 71 years later. Nature was the main journal for publishing scientific, groundbreaking scientific information, and this is even true today. Nature was published in 1869. And what is really interesting about 1953, at that time, there was no peer review, no official peer review. You would send a paper to Nature, the editors will decide, yes, interesting, no, not interesting. If interesting, either they would review it themselves or they would send to some friends to get some advice. So the peer review process, as we know today, and as we discussed in earlier meetings, is undergoing big changes nowadays because of the replication crisis. In 1953, it was very simple to publish a paper. You would send the paper to the editors. If they like it, you were in. And as I mentioned, yeah, go ahead.
May I ask a question, Professor?
Of course,
so-
you guys, just a minute, let's have ground rules. You can always disrupt, ask questions, raise hand, okay? This is
Thanks.
supposed to be a fun course. So no formalities.
So back then there is no checking of the results. Only if you claim that you got good results, it was published.
Do you think there is checking of results nowadays?
I hope to think.
We talked about this.
Yeah, but yet some peer review may be going through the method that one used or something. It was like
Somebody reading. So think about the reviewers. How much time do the reviewer have to replicate everything that the authors did to check that everything is correct?
okay. Yeah.
They're busy.
I-
They're scientists
Mhm.
themselves, right? They
Yeah.
read, they kind of go, they skim through. Some sentences they don't like, they ask to change. Some methods they don't like, they ask to add some control experiments. But who is going to run the code, analyze all the data, check point by point? Nobody. So nowadays, we hope that test of time was not only replication, but test of time. And this is why we require everybody to post the raw data, post the code, analysis codes, that anybody who down the road wants to check can go ahead and check. Because before we couldn't even check. Lab notebooks were lost, raw data was lost, so you couldn't even check. So neither then nor now, people really check for the validity of the conclusions. And what really plays a role here, I think, is test of time. Okay, so we have to understand this. We have to understand how science is being done, but peer review does not prevent from wrong papers to be published. And there are, as I said, meta-science works nowadays show that it's not clear at all what is the value of peer review even today. Okay, it's quite shocking, but that's a state of matter here. So, as I mentioned already, Pauling he didn't know he's in a competition. He was really a very established scientist. He got a Nobel Prize in chemistry in 1954, and he got another Nobel Prize in 1962, and that was a Peace Nobel Prize. Anybody knows why? By the way, his Peace Nobel Prize was in 1962. This is the year that Watson and Crick got their Nobel Prize for the structure of DNA. And why did he lose that competition? Nobody knows. All right. So Pauling was fighting McCarthyism. Anybody knows what McCarthyism is? What is United States House Un-American Activities Committee? All right, so we are switching from molecular biology and science into history. McCarthy was a big World War II hero. He was a general, and he hated communists. And after the war, he was elected to the House, to the Parliament, to the Congress. And he set up a committee, and he was very vocal, and he was fighting communism in the US. This is the beginning of the Cold War. And they arrested the couple Rosenberg and framed as spies that gave the atomic bomb secrets to the Soviets. And apparently later on they were acquitted after they were executed. And many people in Hollywood, many people all over the United States were persecuted as communists and helping the Soviets. And there was a regime of terror in a way, in a democracy, where they were framing, even scientists. So you might have seen the movie recently, The name is I think it got many Oscars.
It was in Oppenheimer also.
Oppenheimer, yeah. I lost the name. So Oppenheimer was, again, McCarthy was going after Oppenheimer. Oppenheimer developed the egg and he was suspected as a communist by this committee. Linus Pauling, as a scientist, was preaching for, free speech, First Amendment. Everybody can do whatever they want in terms of politics, but science should not be affected. But he was suspected by McCarthy as a communist, and for that reason, they did not allow him to go to a very important meeting that was held in UK, where the data was shown. And this is why he lost the competition. So this is resonating very, very well with nowadays politics. The war against Hamas, public opinion, left and right in Israel, and so on and so forth. Just to show you, and nowadays you might have heard about your mentors who are not invited to scientific conferences, or people leaving the room when they give talks, or seminars and colloquia being busted when they go and give talks in other places. Science should not have any relationship to politics whatsoever. This is a person who lost his second Nobel Prize because he was really an amazing scientist because of politics. All right, how many of you knew this story? None. Let's keep on going. So here is a very nice statement. We wish to put forward a radically different structure for the salt of DNA. This structure has two helical chains, each called around the same axis. So they go basically against Pauling. Pauling did not have the data. He made the assumption that DNA is a triplex, basically three-stranded in a helix, a complicated helix. The data was basically showing that this couldn't be the case. He did not have access to the data, so he couldn't correct his model. And Watson and Crick had access to the data, actually not very kosher way. We'll talk about this in a second. And so they could publish the results before Linus Pauling. And indeed, the language they choose here is radically different. It's correct. All the previous hypotheses were wrong. And here comes the common hypothesis was initially that the DNA bases are facing outward of the helix. This is actually a form of DNA that can be achieved today in the lab. It's called bDNA. If you take a double helix and you use optical tweezers and you rotate the DNA, you rotate it so much that the bases flip, they lose their hydrogen bonding, and they flip up to the outside. The initial hypothesis for the structure of DNA was that the bases face the solution. That was discarded. Then there was a proposal for three-stranded, and then came the actual, the real result that it's a double helix, result that hold up to today and really revolutionized the field. So as I said, this is compared to the Newton law, the results stand today. Very, very fundamental paper. And basically they show that the model followed the Feuerberg model. Feuerberg did a lot of analysis and basically came up with some rules about base pairing. So their model was including the results of Feuerberg. And here is the structure. Anybody knows who drew this beautiful hand-drawn double helix? This is not done by PowerPoint or by AI. It's done by hand. This is the wife of Crick. She was the artist for this paper. Another nice anecdote. And here in the paper, they basically talk about base pairing. The rules for AT and GC. One is 3 hydrogen bonds, the other one is 2 hydrogen bonds, and basically they work out And what is really interesting in order to work it out, this is something they borrowed from Linus Pauling. You might know that chemists oftentimes have sticks and balls to model molecules. Linus Pauling was the first to introduce this concept. Here, Watson and Crick basically cut bases from cardboard and try to arrange them in geometry. And they build actually a real size model. It's a very famous picture that you can see in the book of Watson on the cover. Actually, let me see if I can show you this to you just a sec. I need to, well, this is I have background, so I cannot show this. This is the book by Watson, The Double Helix. Very highly recommended. Read for non-experts. Okay, so basically building a geometrical model helped them basically solve the structure. And as we mentioned, alongside the paper by Watson and Crick, there were two more papers. So Nature separately published papers by Maurice Wilkins and Rosalind Franklin from King College, who work independently of each other. The Wilkins and Franklin paper described the X-ray crystallography evidence that helped Watson and Crick devise their structure. The authors of the three papers, the lab chiefs, and the editors of Nature agreed that all three would be published in the same issue. The following communication, so we'll read this paragraph here in a second, that our authors are referring to are the papers by Franklin and Wilkins published on the journal pages immediately after Watson and Crick's paper. So let's go back here into the paper itself. The previously published X-ray data on deoxyribose nucleic acids are insufficient for rigorous test of our structure. One of you mentioned that there is no evidence in this paper. It's just a proposal. So far as we can tell, it is strong. It's roughly compatible with the experimental data, but it must be regarded as unproved until it has been checked against more exact results. So they basically qualify their model. They say it is consistent with the data of Franklin, but it has to be checked further. Some of these are given in the following communication, so they refer to those two papers back to back. We were not aware of the details of the results presented there when we devised our structure, which rests mainly, though not entirely, on published experimental data and stereochemical arguments. So they basically claim that they came to their model without Franklin data, but their model is consistent with her data. So this sentence here, we were not aware of the details of the results presented there, are basically a plain lie. They were aware of the data, and in the paper they say we were not aware of this data. So here we have a big commentary about the story with Rosalind Franklin. How many of you know the story of Rosalind Franklin? You should. She was a Jewish scientist treated horribly in King's College. I'm not going to read everything here, but you know, there are a few points that are really quite amazing. Franklin was frustrated with an inhospitable environment at King's, one that pitted her against her colleagues, and in an institution that barred women from the dining room and other social venues. She was denied access to the informal disclosure that is essential to any scientist's work. She was a woman scientist, not a male. She was Jewish, and she was treated horribly. She was not allowed in the main dining hall of that university. That's quite amazing to read now. And she was an amazing scientist. And she took the data that got Watson and Crick the Nobel Prize, and she was not credited for this at all. Unfortunately, she died at a very young age from, I think, from tuberculosis, sure. But basically, her colleague, Maurice Wilkins, showed the data that she took without her permission to his good friend, Crick. And that basically allowed the Watson and Crick to publish their model suggestion before polling and without giving any credit to Franklin. So this is pretty amazing story. This is not how we would like to think we do science. This is not to say anything bad about Watson and Crick as scientists. They were fabulous scientists. They were very smart. Watson went on to run Cold Spring Harbor for many, many years, did a lot of good science afterwards. And Crick also was doing really well in UK. They were excellent scientists. But this is to show, and we are going to talk for the rest of our course after next week meeting about ethical conduct, about fraudulent science, about your ambition drives you too far. And I would argue that this point where they take full credit for work that was done by somebody else is not good, and Franklin should have been included in the Nobel Prize. Any questions about this? So you can research and find the story of Franklin. You can start with Wikipedia. It's really a pretty astonishing story. And it ended up very sadly. She dies at the young of 43 or something, if I'm not mistaken, without recognition, as a female scientist who have to fight all the time for her position. She basically, when she gives this, I mean, she gives the data to her colleague Wilkins. Without her knowledge, he moves it on. But she gives the data and she's packing. She's leaving the place. The place is horrible for her to work, and she's giving up basically. And here comes a very, very nice, it's a whole paragraph, but it's one sentence. It has not escaped our notice that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material. So the comment here says, this phrase and the sentence it begins may be one of the biggest understatement in biology. Because obviously what the structure did was giving an idea of how DNA polymerase replicates DNA in order for cells to divide. And that was the start of the whole field of molecular biology. And all the way for, coming to the Human Genome Code, Human Genome Project that was completed in the 2000s, and today's CRISPR-Cas9 gene therapy. This is all coming from this replication mechanism here. And here there was a question about providing evidence for the model. So it was really a proposal. We talked last time about a model for peer review where you can basically just publish your plan to do experiments and you list what you do, or some kind of a plan for a proposal. That's what they've done here. In this paper, they just come up with a suggestion for a structure, and they say, we will have a detailed paper following, and that was very common at that time. You would publish a one-page kind of a big statement, and then you follow up with a detailed paper after, which indeed they did. In 1954, January 1954, they have a paper that you're missing, the paper that basically provides all the evidence for the proposed model. All right, so that was going quickly through the paper. There is a very nice paper that is not really a scientific paper. It's more like philosophy and ethics. And this is really about creating an ethos, because obviously this double helix paper became an ethos, like Newton, laws of motion. And this really, if you're interested, you can look into this. It's The Birth of Molecular Biology, an essay in the rhetoric criticism of scientific discourse. So worthwhile looking at this. To conclude, this is a paper that Tobin wrote 50 years after the original paper. And what are the lessons? We have 3 papers back to back. First lesson, collaborating with faculty colleagues is more profitable than competing against them. Second lesson, research has no value if unpublished. And third lesson, Watson and Crick have something important to say. They say it clearly and then shut up. The article exemplifies the 3 cardinal qualities of good scientific writing: brief, clear, and simple. All right. Any comments about Watson and Crick, double helix, thoughts about Rosalind Franklin? Anything? Really nothing? How many of you knew the story? None. Okay, let's move on. This is a much harder paper to read and longer.
Introduction is count.
Sorry?
Reading the introduction and summary counts.
40%.
Hmm.
I think you need to read not only the abstract, the introduction. Did you read the introduction? At least it talks about what it is all about.
Yeah.
Yeah, okay.
Introduction and
All right, so you can vote yes. Anybody else? I know I made a mistake. I announced this only yesterday, so I didn't give you enough time to read. But I want to know if others have read it. Okay, only 2 of you. All right. The reason, so Watson and Crick, of course, I think is a paper that every scientist should read regardless of your field. Forrester is kind of more focused, and if you're outside the field, I'm not sure it's going to contribute a lot, but nonetheless, I want to go over this because next week we are going to talk about my own scientific career a little bit, and Forrester has to do a lot with this. And it's also, I think, a very, very important paper that you should all be aware of. Even if you're working on excitons in graphene, Forrester energy transfer mechanism is very much related. So let's start. Okay, so this is the paper we're discussing, published in 1946. It's a theoretical paper, and it came to answer an important question. So here is the German version of this paper, and it was translated in 2012. Basically, this is the original paper translated into English and published in the Journal of Biomedical Optics. The title is Energy Migration and Fluorescence. What is the relationship between energy migration and fluorescence? Until then, people are most common to think about electron transfer as a mechanism for energy migration. And for that, you need to have some kind of a molecular wire that, like if you're talking about semiconductors, you have hybridization of the conduction band orbitals, and you get basically a band where electrons can migrate from one nuclei to another. So there was a lot of work done on electron transfer, but what we are going to discuss here is something very different, and there was no good explanation. Further theory and the accompanying experimental work on energy transfer is the most widely known and most influential of all Fred publications. Forrester provided an accessible theory in a form that was practical for experiments. It is difficult to exaggerate the influence of this work. The extensive, widespread use of Fred in physics, engineering, chemistry, biology, and medicine are due to the description of energy transfer given us by Forrester. This is basically written by a friend of mine, passed away many years ago, Robert Clegg, who actually knew Forrester. He did his postdoc in Germany and stayed there. He is an American. He wrote a book, The History of Fred, and this is basically a chapter on review of fluorescence. Anybody has an idea what Fred stands for? What is the acronym? So there are two competing versions. One is Forrester resonant energy transfer, and the other one is fluorescence resonant energy transfer. And in fact, there is a debate in the field right now. People don't like Forrester resonant energy transfer that much because, anybody has an idea? Forrester was a member of the Nazi party and collaborated with the Nazi regime during the war. So this is why there is a movement to really stick only to one acronym and not the other. Just again, how politics and science touch each other. Another example. So for the two of you who read at least the introduction, what was Forrester's motivation to study energy transfer or energy migration? You can use 3 words in your Mentimeter response. Nothing? So I take my 40% back, maybe 25%, if you cannot give an answer. But the answer is in the introduction. All right, let's move on. It's not what I wanted. Okay. So the answer is basically photosynthesis. There were some experimental results that were very, very puzzling. People identified reaction centers in leaves, and the concentration or density of reaction centers did not make sense. The energy balance, the amount of sunlight that falls on the leaf compared to any reaction center you have, shouldn't give you enough photosynthesis. And there was a detailed balance that they tried to work out. And basically, Forrester was the first to come up with the idea that there are many, many antennas that funnel all the energy into those few reaction centers. Only then you can actually balance the reaction. So it was a very important question, very relevant today as well. The question was about photosynthesis. All right, so Forrester apparently became interested in the energy transfer process because of the known effectiveness of photosynthesis. Although he was also aware of Perrins, Perrin did all kinds of interesting quenching and depolarization experiments in the 20s and 30s. Experiments by Emerson and Arnold had shown that the capture and utilization of light energy by plant leaves was much more effective than would be expected if it were required that photons exactly hit the reaction center. That is, there are too few reaction centers in the leaf to explain the very effective extent of energy capture. So if you are trying to build artificial solar cells that harvest solar energy and produce electricity, you face the exact same problem. And you will have energy transfer in those structures as well. The idea is to have a very large effective area capture of an antenna that can funnel this energy to the place where you want to build your battery or whatever. That's exactly what the plant leaf does. I'm not going to read this paragraph that is taken directly from Forster paper, but exactly here he discusses this discrepancy and the need to come up with a different concept, because basically you cannot balance a reaction unless you assume you capture much more. The effective cross-section for capture the sun is much higher than just the cross-section of the reaction center. And that basically leads to the idea that you have many, many antennas for each reaction. All of them absorb lights, and they transfer the quanta of energy into the reaction center. Forster knew of these results and reasoned that an externally efficient transfer of energy between the chlorophyll molecules must be responsible for the eventual diffusion of the energy, which was over the whole surface of the leaf into a relatively sparse reaction center. He assumed that this energy diffusion is due to energy rapidly hopping between molecules. He was also aware of the earlier work of Perrins. This is father and son worked in Paris at that time in the 20s, 30s, and they worked on molecules in solution. And they did basically energy transfer experiments, but they have not really understood fully what they're observing. And of other data indicating energy transfer over distances longer than the molecular diameter. Basically, until then, quantum mechanics was already in place, and people understood that energy can transfer when you have wave function overlap. But you cannot have any energy transfer if you don't have a wave function overlap. And Forster was the first to actually propose a mechanism that it can happen. So nowadays we have crystal structure. You here see crystal structure of photosynthesis systems. You have those antennas. Those are little chlorophylls. They capture the light, and through energy transfer, they move it to the reaction center. Here is another system. We have now detailed atomic level structures, and you'll see some predictions that were made basically in 46 and moved only after, 60 years. Here is a better depiction of one of the systems. You'll find it in leaves, you find it in algae, you find it in many, many different systems. That's the basic mechanism. You have many antennas that capture the lights and transfer it to the reaction center, where actually the electron-hole pair separation, if you want, happens. However, it has to be pointed out that the existence of an assimilation unit, and therefore energy migration in this assimilation unit, is very controversial. So that's in his introduction when he basically suggests this. Forster then brings other non-biological electron transfer examples. And he basically claims that the same mechanism that happens in photosynthesis also happens in sensitized photochemical reactions, in concentration-dependent depolarization. Those are the pairing experiment, and concentration-dependent quenching. And he adds, it is now mostly assumed that in biological processes, the energy migrates without being linked to a material carrier of any kind. Basically, the term that is coined is radiation-less electron transfer. So think about a radio station. You have two molecules. One absorbs the energy with a higher photon energy. So let's say in the blue, green, or UV. You are in the excited state of that molecule. When the molecule is in excited state, it's basically have free induction decay. It radiates like radio waves, but it obviously at a very different frequency. And you have an antenna. An antenna basically absorb this electromagnetic radiation and convert it into basically electron hole pair. So that concept of radiationless energy transfer, it's just through electromagnetics, was a new concept. So here is the situation that we have. We have two organic molecules with manifold of states. Here we have a ground state, and here we have many excited states. This molecule we call a donor, and this molecule we call an acceptor. You see that the energy level alignment of the acceptor is lower energy than the donor. We have the sunlight, or in modern experiments, laser light, that basically promotes the donor from the ground state to the excited state. So ground state is D and excited state is D star. And energy can basically transfer through this radiationless energy transfer through electromagnetic. There is no real emission of a photon here that then excite this molecule, basically emission and absorption. That would be energy inefficient because you have many losses along the way. And the radiation, when you have a real emission, is going in all directions, like a dipole antenna, and the cross-section will be very low and you won't capture much energy on this molecule. It's really the fact that you have this radiationless energy transfer. The acceptor is the same, ground state A, excited state A star, and basically all the possibilities are written here. You start with donor and acceptor in the ground state, you add one photon, and then you can get an excited donor plus the acceptor, which can transfer the energy to the acceptor, and then you have ground state donor and excited state acceptor. That's a process we are looking at, and the rate is K sub T. There are many other processes which are basically not contributing for energy transfer. You can have radiationless relaxation to ground state from the donor, or radiationless, what we call non-radiative decay, due to basically generation of phonons of heat to the ground state of donor and acceptor, both from the donor or from the acceptor. Or you can have just the excitation by emission of photons. So that would be a radiation relaxation. So donor can emit a donor photon and go to the ground state, or acceptor can emit an acceptor photon. So basically, we are interested in this process. We will not work the theory, but basically Forster shows in his paper that the efficiency of that process going from here to here is this KT transfer divided by the sum of all the other rates. The transfer plus the radiationless and the radiation de-excitations. And this property is basically dependent on distance between those two molecules, like 1 over 1 plus R to the 6th power. R here is normalized by a factor called R naught, which is a Forster radius. We'll talk about this in a second. But basically, you have a very strong function of distance between those two molecules. So if the two molecules are very close to each other, energy transfer is very high. And if the two molecules, so basically if R here goes to 0, you have an energy transfer 1. If R here goes to infinity, energy transfer goes to 0. And so it goes between 0 and 1. In other ways, you can describe the same formula as the rate as one of the excited state lifetime of the unperturbed donor, multiplied by this Forster radius divided by the distance to the 6th power. So again, you see this 1 over R to the 6th power dependence on the rate. So again, this is again what we call a Jablonski diagram for donor and acceptor. We are interested in this FRET process. So you can excite the donor can emit or transfer energy to acceptor. And if acceptor is excited, the acceptor can emit. If there was no energy transfer, you'll never see an acceptor photons because the acceptor is not excited. Only if there is energy transfer, you'll see some acceptor photons. As we said, this formula that describes the efficiency of the process, strongly dependent on distance. Here is that dependence. So energy transfer goes between 0 and 1, or 0 and 100%. And it is a very strong inverse sigmoid, where 50% energy transfer is called R0. That's a parameter, we call it Forster radius. And that is a function of the two dyes and many other things. We'll go over that in a second. So if you have different donor-acceptor dye pairs, this function can basically have different R0s. So here you see a family of curves with different R0. What is interesting really is this linear part of this sigmoid, because this linear part tells you that energy transfer can be used as a molecular scale ruler. You can actually measure distances along this linear part of that curve. And this is very significant because now you have a way using optics and lasers to actually measure distances in molecules and in atoms. We talked about R0. R0 is a function of J. J is something called the spectral overlap, donor quantum efficiency, the index of refraction of the media, and kappa square, which is called the orientational factor. So first, the spectral overlap. The spectral overlap is basically the overlap between the, so here you see a spectrum of a donor and acceptor molecule. In dashed lines, you see the absorption. In solid line, you see the emission. So this is basically stock shift. The emission is always stock shifted compared to the absorption. You see here a dye called TMR. And the spectral overlap is basically the overlap between the emission of the donor and the absorption of the acceptor. This is the hashed line here. That's a spectral overlap. It's basically the multiplication of FD of lambda, that's emission of the donor, times the absorption of the acceptor, times the wavelengths to the fourth power, and you take the integral. So this is the spectral overlap that can be calculated. Basically, if you take any of these dyes here in the list, you can calculate what is the spectral overlap. You can plug in the wavelengths and so on. So here you see a list of Forster radiuses for different pairs. So when you want to actually measure distances, you need to pick up donor and acceptor pair, depending on what kind of range of distances you want to measure, because as you see, the linear part of this curve is not too large. You have about 20, 30 angstrom to be able to measure, and you want to pick up which of these curves is relevant to what you want to measure. So here is an example of pairs and radiuses. The orientation factor is that both donor and acceptor are dipoles. If their dipoles are fixed, it really depends on what the directions is, and the efficiency of energy transfer is strongly dependent on this. This factor is given here by these trigonometric functions, and it can go anywhere between 0 and 4. So identifying what kappa square is very important. If the dipoles are fixed and not rotating, it really messes up your ruler. Your ruler is no good because it's very hard to know what kappa square is. But if you know that the two dyes are tethered to two sides on your molecule and they rotate really very fast, you can do actually averaging. And if you do this averaging, kappa squared takes the value of 2/3. And then you can actually use this as a ruler. This is just to show that kappa square really can go between 0 and 4. If the two dipoles are parallel to each other, you get the maximum transfer. Parallel in this arrangement. If they are parallel like this, it's 1, and if they are orthogonal, it's 0. And most likely, if they are freely rotating, it's 2/3. There are three main ways to measure energy transfer for ensemble of molecules. One is you just look at the spectrum of the donor, and once acceptor is present, the donor transfer energy to acceptor, so the donor emission itself is reduced. So you're basically analyzing how much reduction in the donor emission you have. This is written here. That's one way. Another way is to do time-correlated single photon counting measurement, where you look at the excited state lifetime of the donor. And you have two samples, one donor without acceptor that gives you the original lifetime, and then you add the acceptor and you get reduction in lifetime, and then energy transfer is given by this, the unperturbed lifetime divided by the perturbed lifetime. And the third option is actually to look at the intensity change of the acceptor. If there is no acceptor, there is nothing except for maybe, or if the acceptor is very far, you have something called direct excitation. That laser that excites the donor also slightly excites the acceptor, because there is a tail for the absorption of the acceptor. And then if there is energy transfer, you get much more intensity, so you can calculate this ratio and extract the energy transfer. Once you extract the energy transfer and you know the R naught, you can also basically calculate what is the distance between the 2 points that you are interested in. So Forster concludes, however, conditions are conceivable which even in high concentration do not allow associate to be present or to be formed after excitation. It would only be required that each chlorophyll molecule is sufficiently deeply embedded in a corresponding protein, or that it is bound at a defined position of a protein structure. However, a quantitative treatment of such a model on the basis of theory developed here appears not yet possible for sufficient data. So basically, he makes here a prediction that the chlorophyll, there are many chlorophylls arranged in a protein structure around the reaction center, and 60 years later, that structure was solved. So this is really quite amazing. All right, we only wanted to demonstrate that this type of energy migration in non-biological systems is more frequent than generally assumed, and that by and large, it is a phenomenon which is theoretically understood. To summarize first the paper, Forster theory is the basis for our present understanding of threat and most of its applications. Within the validity of the model, which encompasses most of the applications, Forster's original theory still applies. Theory has been tested thoroughly, and if the conditions for which his derivation is applicable are met, the theory has always been found to be valid. Original theoretical description of energy transfer sets the stage for all subsequent application of threat in many fields. The extended of the original idea of pairings, Jean-Baptiste and Francis, involving the well-known interaction of molecular dipoles. However, his insight and great contribution was to provide the quantitatively correct and very practical description of threat process in terms of experimentally accessible parameters. He really made that translation from a concept to a place, to a point where you actually have a ruler and you calculate distances on the molecular scale. Threat has been shown to be broadly applicable and extremely informative for determining molecular interaction and to measure molecular distances that are impossible to determine otherwise. So it's very important for structural biology, and in practical manners, many drugs, when they screen libraries of small molecule drugs, they actually use threat as a readout method. We'll talk much more about this next time, but this is for today. Questions? So I know that we are going quite far from physics, but again, I think it's important. Next time, we'll talk about my own research, and you're going to get this week homework. I'm going to give you a paper to read and answer some questions, and I'll give a deadline. The deadline will be basically next Sunday. And after that, we are moving into a very famous case of fraudulent science. And in 3 weeks' time, you guys will start to present. So not all of you filled up the Google Sheet, and you have not approached me with ideas for your presentation. Time is running out. I expect everybody to do this. Any other comments? If no, then good night for everybody. I'll see you next week.
Bye.
Thank you.
Good night.
Yeah.
Thank you.
Good night.
Yeah, thank you.